All right. Move this over. Okay. So I was unsuccessful in finding a person to come and present. So therefore it defaults to me this time. And so
Yeah. Again?
again. So I thought what's the next project that I'm thinking about? And so I thought, oh, well, let's talk about square antennas and actually four square antennas. And generally they're used for the lower bands, so 160 meters, 80 meters, 40 meters in some cases. Some people have even made them for 20 meters and even 30 meters. Um, they're much smaller in that case, easy to handle, fairly easy to put up. But I thought I'd talk about 80 meters because most people that have an 80-meter antenna, it's usually a dipole or an off-center fed dipole, or perhaps an in-fed of some sort, and or some shortened base-loaded type vertical antenna. And so I thought, well, maybe let's talk about four square antennas where you can actually get some directivity and you can effectively point the antenna to a particular location on the planet and get some good front to back ratio so that you can hear people in front of the antenna versus blanking out the people behind you. And so you can typically get about 15 to 25 dB front to back ratio depending on how you set the thing up. And the antennas don't physically move, they stay in position, but you use the spacing between the antennas and the feed phase angle. So depending on which antenna you're driving at what phase angle will determine which direction the antenna is actually pointing. So we'll go over some of that. And so I found on the internet on Dave's QRZ page, he had a nice picture of an 80-meter four square out in his pasture. And you can see there's four vertical antennas here. This one's kind of hard to see. 2, 3, and 4 over here. And for some scale, there's a person standing over here. He's probably 5'6" to 6 foot tall. So it gives you some idea how big this is. Typically, they're a quarter wavelength in length. The height is a quarter wave, and then the spacing is usually a quarter wavelength. But you could use a half wavelength that just changes how you have to phase the antennas to get it to point where you'd like the antenna to transmit to and where you get the best receive. But we'll go over some of that here in just a bit. So let's. Is what? Yeah, good question. So in this case, the entire pole, the entire vertical pole is the antenna. And if I remember right, this is the DX Engineering antennas. And so they have a really nice setup for putting up an 80-meter vertical antenna. And the poles start at 3 inches in diameter, and then they taper up to I think it's 5/8 of an inch, or maybe it's 3/8 of an inch. I forget now. But they're concentric poles that are bolted together, and so it gets smaller and smaller as you get closer to the top. And they're for 80 meters, a quarter wave is about 67 feet. So they're pretty tall. They have 3 different versions. So I think the mid-scale version that I'm looking at is rated for 90-mile-an-hour winds, unrestrained, so no guide wires, no guide ropes. But if you put guide ropes on it, it should handle well over 100 miles an hour with the wind. So well, you'll get to see how they isolate it from ground. Yeah, so we'll get to that. So, you know, for 80 meters, I mean, 80 meters, that's pretty far. It's a quarter wave is 67 feet roughly for the middle of the band. And so just how big is it going to be to space out all these antennas? And since I'm going to make the assumption we're going to look at a quarter wave spacing between the antennas in both directions, X and Y. And then that means with the radio field, that's another quarter wavelength on either side. So it's 3/4 of a wavelength or 60 meters. And so that's almost 200 feet on a side to get all the radials and the antennas to fit on a piece of property. Well, an acre is 43,560 square feet, which is a little bit over 200 by 200 feet. So about 1 acre is what you need to put one of these antennas up. So you need a small piece of a parcel of land away from everything. Hopefully there's no buildings close to it, because they'll couple into the signal will couple into the buildings. But in any event, that's why not everybody has one of these put up on their city lot. Your house can't be in the middle. It would drastically reduce the performance of the antenna. But so it's pretty big, about an acre.
Ground radials, are they all common ground or the four separate?
Yeah, so that's a good question. All of the radials, so the reason I drew in the plus sign between the antennas in gold or amber color is because what you want to do is you don't want to overlap the radials on top of each other, because you don't want to have different grounds. You want one ground plane all at the same voltage. And so those amber, the amber plus sign represents copper that you solder the ends of the radials to those bus bars. And so you make a complete ground plane solid over this 1 acre patch, or nearly an acre patch. And so it operates as one ground system. Yeah, you probably need a lot of propane, or if you're using electricity, bring some gasoline for your generator. Yeah. So the antenna itself doesn't rotate physically, but it rotates in phase space. And so by controlling how far apart the antennas are and what phase you feed each antenna, you can control the radiation direction. And a lot of people just set them up as a simple Foursquare with a simple hybrid coupler, and then you get 4 directions pretty easily. And most people set it up, I think, for shooting off the corners. So, antenna 2 and antenna 4 are lined up together and it shoots off to the northeast, or you shoot off to the northwest or the southwest or the southeast. But you can, by changing the phasing and using a different method of hybrid coupling, you can shoot off the side of the antenna. And so you can feed antenna 1 and antenna 2 at minus 90 degrees and feed antenna 3 and antenna 4 at 0 degrees. And now you'll get what's called in fire. And so it'll shoot straight off to the north. And it's a little bit less gain, but 9/10 of a dB here or there, it's better than a dipole. And it has a much lower radiation angle at 21 degrees compared to a dipole, where the dipole, you'd have to get it at least a quarter wave in the air. So the entire dipole would have to be at 67 feet or thereabouts, at least, if not higher, half a wavelength, in order to get a lower radiation angle, so that you can get a long skip for chasing VX. So this is a lot of junk to make this thing work. The real magic happens in that one little box called the RF network. That's where all the coupling takes place between your transmitter and the switching the antennas to feed them with the proper phase angle so you can control the direction. And we'll go through the what's inside that little box a little bit later. But this particular coupler is set up so that you can shoot the antenna at 8 different directions. So the gain's a little bit different, but the front to back ratio is still about 20-1. So about 20 dB front to back. So effectively you're blocking out all the signals behind you and listening primarily to the people out in front of the antenna at about a 60-degree angle. So it's pretty wide. It's not very narrow. Of course, you're not getting a tremendous amount of gain, but you're effectively doubling your power. So you have more than 3 dB of gain. So if you're feeding in 100 watts, you're radiating roughly 200 watts. You know, if you're running 1500, you're running basically 3000 watts in the direction of transmit. And so since it's reciprocal, you get that gain on receive also. So it's part of the advantage of having a gain antenna. Oh, and the other nice thing I saw on this was that, you know, most people, I think, set their four squares up so that they're in the non-powered position. It's pointing to the northeast. So if for some reason your power supply that's switching this thing around happens to fail and you lose power, you'll notice that the northeast line here that runs through the controller, it's powered with what V plus here, whatever the voltage is needed to energize these relays. There's no diode matrix connection. So if you lose power, that is the default direction. So it'll always point towards the northeast, which just for the United States, that's basically Europe. And so there's hundreds of part of the DXCC entities. A lot of them are in Europe. And so anyway, I thought that was interesting that you didn't have to have power to make it work there.
Set yours up if you're going to do this. Four notes that connect with north, east, south. Are you going to align it to the magnetic compass so it does that, or are you going to spin it? You can kind of
to the
when it falls northeast, it's really
yeah. So I'm
east or more north.
Yeah. So I'm not going to line it up to magnetic north. I want to line it up to true north. So depending on whatever the declination is down there in Cochise, I'll have to look on a map and see what the declination is currently, because it moves as the magnetic pole moves. But yeah, to use a compass and then offset it by whatever to get true north, so that it'll point towards Europe when it's northeast. Yeah. So this is what the base looks like. How DX Engineering wants you to put it into the ground. Now remember, this is a 3-inch piece of aluminum pipe. It does taper, but it's fairly heavy, and so they have you put in a substantial piece of hardware into the ground, 2 foot by 2 foot square, 4 feet deep, buried in concrete. And if I remember right, it's a 3-inch pipe. Actually a 3-inch tube, not a pipe. You want to use tubing because if you use pipe is doesn't have a lot of tensile strength. It may be okay for making horse fences or cattle fences, but it'll bend pretty easily. Tubing, on the other hand, has a very high tensile strength because it's extruded and or rolled and then welded, seam welded. And so it makes it much, much stronger, so it doesn't bend nearly as easily. So the the whole concept that they have is that this assembly down to the right, it's all made so that a single individual can put this all together and raise the antenna. You don't need any other people unless you want somebody to chat with and help you put up the other 3 antennas. but it's made so that you can crank it up by yourself and put everything in place as a single individual. And so this is the base piece. It has a winch that you can move from one vertical antenna to another, and the base piece will tilt out and allow you to lay the antenna down flat on the ground, do the assembly, bolt it in place, and then crank it back up vertically and bolt it in place here on this bracket that mates up here with this set of U-bolts and framing, and to hold it in place. And so cranking on the winch, people that I've seen on YouTube, it's really easy to crank it up. And then you can take the winch off and lock everything in place, bolt it down, and put the winch in your storage shed until the next time you have to take it down. So the vertical piece is not grounded. That's the driven element. And so the radial's attached to the plate at the bottom, because you see there's a radial plate that has a whole bunch of holes around it at the bottom. So I think that plate has 60 or 64 holes in it for putting radials out. Yeah, so the gray piece, you're right. This gray piece is some sort of fiberglass and carbon mix. So it's an insulator, and it insulates the pole from ground. So it has separate attachments down here that are not connected to the pole, so you can drive the pole with your transmitter.
And then that black pipe is what goes down.
Yeah, so this pipe here is the one that goes down inside the into the concrete down below. 4 feet, and roughly 3 feet is sticking out of the ground.
What was the square?
It's 2 foot by 2 foot, 4 feet deep. Yeah. So it's a pretty substantial block of concrete. So, if you're going to put down 60 radials for each one of these antennas, and you got 4 of them now, how in the world, you don't want to just toss them out there for this. You kind of want to spread them out somewhat evenly, because you want to get the maximum gain possible. And so if you do a quarter wavelength, roughly 65 feet, 67 feet, turns out you can calculate what the chord length is. So somebody a long time ago figured out you can compute what this distance is. Now, of course, at 65 feet, it's going to be pretty short by by comparison. And so it turns out that the straight distance from one wire to the next is almost 7 feet. And so you can string out one of your 65-foot radials and then tie a string. So twist the end of a screwdriver, tie a string to it that is nearly 7 feet long, and measure out where the next radial should go, and then pull the next wire out, tie it off to a nail. I've seen people use these large nails. I don't remember what size they were, probably 6 penny or 4 penny, huge nails, 6-inch nails.
You think these toilets have enough of?
Yeah, I can use toilets. Yeah, make a ring of toilets. Exactly. We got a place to sit. Yeah.
And if you need to take care of it,
You can do it right there. Yeah.
Sorry, I brought that up.
no fun intended.
So yeah, there's a bunch of wires. So if you do 60 radials on each one, that's 4 times that, 240 wires to be strung out. And remember, there's a lot of soldering that's going to be involved, because you have to solder each one of the radials that go towards the center, towards one of the other verticals. you need to solder those to a bus bar so that you tie it together as one ground system. So it doesn't necessarily have to be solid wire. It could be stranded. But people have used anything from 16 gauge through 10 gauge. It doesn't seem to be a lot of for the radials. Yeah, for the bus, people have used, I think, the bare 10 gauge to solder to. The few anecdotal comments that I found, there's not a huge amount of difference for the radials on gauge size. They didn't notice a lot of difference.
It was a hard test, right?
It's a big investment to do an A versus B. Yeah, exactly. Yeah, yeah. So I think people just get whatever's the cheapest at the time and whatever they can afford.
What they're gonna do?
So I've been debating on whether I'm gonna run 14 or 12 gauge wire. I don't know if it's gonna be stranded or not, if it'll be solid. But I've also considered using fencing. So like sheep fence or goat fence. Basically something that looks similar to chicken wire. But a little heavier than chicken wire. Yeah, barbed wire. Yeah, use barbed wire, right? But you can buy that fairly cheap in rolls, in 100-foot rolls, 5 and 6 feet tall, and
You get about 3 miles of it.
yeah, whatever it is, and you need a lot of it. Yeah. So I don't know. I'll have to weigh the costs and what I think the advantages may or may not be for the radial system. But so I thought I'd start off by going back to Bill Orr's book from 1959. He's of course passed away now, but I think he passed away in 2001 or 2003. But he published a lot of articles in Ham Radio Magazine, if anybody remembers that publication from the 60s, 70s, and 80s. And he published a what he called a radio handbook, and I brought mine tonight. It's the 23rd edition. I think this was published in the late 80s. But it's a handy book to have. He goes through all the basic calculations for various whether it's transmission lines or antennas or radio circuitry. He takes it right down to the nuts and bolts. But I thought I'd share, if you have 2 antennas, something simple to think about in phasing. And so if you have 2 verticals like on the left, figure A, and so 1 and 2 represent, those 2 dots represent the verticals looking down from the top. And if you drive them with quarter wave coax, so you have a feed coax coming in here from the bottom, and it's in the hooks in together in a T at the center between the antennas. You have a quarter wave on each antenna, so it's the antennas are spaced a half wavelength apart, and they're quarter wave vertical antennas. Well, this is the radiation pattern you get. You get a figure 8. And so you get some directivity, no front to back ratio, but you do get front to side ratio. And so there's no radiation going out to the sides. And you have equal gain in the forward direction and in the reverse direction. If you change how the thing is fed and you still have the same half wave spacing, but you feed it from one antenna and all the way across to the other antenna. So now you have a half wavelength half wave spacing and half wave phasing. That combination gives you radiation off to the sides, but very little to the north-south direction. So you just by changing how they're phased, you can point the antenna to some degree. if you to change your spacing just a little bit, make it a quarter wave instead of a half wave. And so now you have a quarter wave spacing and a quarter wave phase shift. Well, now you get something that looks like a cordia wave. And so now you're getting some front to back ratio because there's little signal going to the left, but quite a bit of signal going to the right. Now it's pretty broad. I mean, there's only 2 elements. So the 3 dB bandwidth, or not bandwidth, the 3 dB points off of this gain plot are pretty far apart. So it's like 90 degrees is the beam width, effectively. And so we're not getting a huge amount of gain, but it's better than a dipole at 20 or 30 feet, where almost all your gain is going straight up in the air, near vertical incidence spectrum. So this is just from Bill's book, all the different combinations. So if you, across the top, if you change the way you phase the 2 antennas, and then going down from vertical, if you have half wave space, quarter wave space, eighth wave space, depending on how you feed those 2 antennas, you can point the radiation pattern to where you desire and can have some control over the front to back. Now, again, this is only for 2 antennas phased together, and you're probably not going to move them physically. So changing the spacing is, once you've set it, you're probably not going to change it, especially not between contacts. That would be a bit of a chore. But you might be able, with a phasing network using lumped components, actual coils for inductors and capacitors, you might be able to change the phase with the components rather than transmission lines. But you probably will not get all of these different phases because in some cases, the spacing will be physically bigger than the phase length of the coax. So there are some of these cases that would be impossible to achieve. Okay, so how do we start to phase these things? So the hybrid couplers that people design, they're actually 100 ohms at the port. So the transmitters are all designed for 50 ohms on the transceiver. And so you would like to feed it with 50 ohm coax. But when you feed that into the hybrid coupler, it has 2 transformers inside. And the combination of those gives you an impedance looking back towards the transmitter of 100 ohms. And so, or sorry, not back to the transmitter. The transmitter looks at, is seeing 50 ohms, but on the antenna side, it sees 100 ohms. And so at the coupler. And so now you have to match 50 or 100 ohms to 50 ohms at the antenna. So you end up tuning each antenna separately. So you take your antenna analyzer, your Rig Expert, or your MFJ device, or your Comet device, and walk over to the antenna and hook up your coax. Step back away from the antenna, at least an eighth of a wavelength, maybe a quarter wavelength, and take your measurement and tune your antenna using 50 ohm coax, because your coax is most likely going to be 50 ohms, and the antenna should be pretty close. If you have a very good ground field, if it's a perfect ground field, you should end up with about 35 or 36 ohms of antenna impedance, and then it's a matter of using a coil to shift that so you can get it to 50 ohms at the base of the antenna. So once you have 50 ohms at the antenna, but you have 100 ohms at the RF network port where the hybrid converter is, you need to use a piece of 75 ohm cable. Now, the actual value that you should be using is 71 ohms, but nobody makes 71 ohm cable. So 75 ohms is close enough. So there's going to be a little bit of mismatch. There's going to be a little bit of mismatch because the antennas aren't perfect. There's going to be a little bit of mismatch because of this difference between the hybrid converter and the antenna impedance. So there are some losses in here, but they're minor for the most part, or they should be minor. So the antenna, well, we know that it's this quarter wave spacing around the around from each antenna, and you're using this 75 ohm cable to make the connections between the hybrid converter in the middle and each antenna. So if you try to use 50 ohm cable, you could try that, but you'd find that a piece of coax for a quarter wavelength for that that distance, your coax would be too short, and so you couldn't make you could make the connection, but it would be even higher mismatch and more loss. And so that's why people use foam-based higher velocity factor above 80, above 0.8, 80%, and 75 ohm coax to make that interconnect. The cable going off to the transmitter is standard 50 ohm cable, and pick your pleasure of what you'd like to use for that, RG213 or LMR 400 or LMR 600, or depending on how far away the whole thing is from your shack. One thing that you probably notice is that there's a dummy load out there right next to the hybrid converter and or the hybrid bridge. And why in the world do you have to have a dummy load out there? And it's connected all the time. So it's not like you're switching that in and out. It's actually part of that hybrid combiner out there. And so this is a part of what's inside that hybrid combiner. And this is actually for a two verticals. And so the feed is off to the left, up there where it says the 3 dB coupler by Reed and Fisher. That's where you connect your transmitter. And you have a transformer. So you have a toroid core that you wrap L1 and L2 around. And you have a few capacitors there. And antenna 1 and antenna 2 are on opposite corners on this hybrid bridge. And the dummy load connects to the fourth port. And so when you put in power on the number 1 port in the upper left, I'll call it the number 0 port because they label it out 1 and out 2. If you put your transmitter power into port 0 in the upper left, you'll get half the power going out to output 1, antenna 1, and half the power going out to antenna 2. And any mismatch between those antennas or the feed cables, that energy has to go somewhere. That imbalance, that power goes into the dummy load on port number 4, where it says type D over there for a dummy load. And so what you're optimizing for is that the dummy load power is as low as possible, which means that you have the best match possible for antenna 1 and antenna 2 with the hybrid coupler providing the phase shift between those two antennas. Now this here is just for 2 antennas. So the phase shift is 90 degrees between antenna 1 and antenna 2, which is a quarter wavelength. And so that's how you get the particular pattern for two antennas phased together. Yeah, so the question was about the capacitor 1 and capacitor 2 versus L1 and L2 and the coupling factor between those two coils. as a transformer. All three of those, or yeah, three of those values contribute to the balancing and the frequency spread. And that's actually a good lead into this, which is the simulation of that hybrid coupler. And so you want the phase shift to be 90 degrees or quarter wave across the entire band, or you'd like it to be across the entire band. So this is for 80 meters. So all the way from 3.5 megahertz down here, all the way up to 4 megahertz, it's always 90 degrees from this line to this line. The two horizontal lines, or nearly horizontal lines. So it maintains phase shift properly across all frequencies of interest. And the gain difference is pretty small, about half a dB. This was done by an Englishman, so there's commas instead of periods. Yeah, it's a little less than half a dB difference as you move from the lower end to the higher end of the frequency band, which is pretty good to have such a small shift. But the phase angle is the same, which means that no matter which frequency you're on, your antenna is always pointing in the same direction, the radiation pattern. So how do you do this for 4 antennas to phase them all together? So we have the same coupler. So we have our 90-degree phase shifter up here. And then we add another phase shifter. This is our dummy load. So they just show, well, okay, 200 ohm resistors in parallel. Make sure they can handle about 50 watts so that you can dissipate whatever mismatch power happens to come out to it.
And that's for a kilowatt.
No, I don't think this needs to be a little bigger, because the mismatch, you could have about 10%. So you need something that can handle about 150 watts. So a 250 watt dummy load should be sufficient to run a kilowatt. So you have the original hybrid coupler up here. And if you tie that together with another transformer, another hybrid coupler, but this time you don't use capacitors, you ground the opposite ends. So you ground the two ends, the two ports that are diagonal to each other. That gives you 180 degree, that gives you a 90 degree flip. So here we have 0 degrees at the top. Here we have 90 degrees. So we picked one off of here for plus 90, but we need minus 90 on the other side. So we get that over for the other side of this. We get 100 ohms that we're now feeding to the antennas. And then this switch matrix of relays does the switching between which antenna gets driven at plus 90, which one gets driven at minus 90, and which one gets driven at 0, or pairs of antennas. And so by the change in those combinations, I think, is it the next slide? No.
Apparently not.
Apparently not. Oh, I think I had it in the beginning. Here. So this massive matrix, K1 through K6, are all those relays that control which antenna is hooked up to which phase angle. And so it then tells you, okay, which phase. So for this configuration of switches, it gets us the north direction. So K1 and K4 are turned on. K5 and 6 are off. So K4 and K1 get turned on. That's antenna 1 and antenna 4. Well, antenna 1 and 4, yeah. K4. Yeah. So what it does is it forces the phase angle on 1 and 2 to be minus 90, but on 3 and 4 to be 0. So that you're shooting off your end fire. It's like having 2 vertical beams with just a driven element and a reflector facing in the same direction, that are phased a quarter wave apart because of physical space. So you're getting gain from that. So this is the magic that's happening inside the box, the RF network box, is this being able to shift the phase to the proper angle for each of the antennas. And so you can simply rotate this switch, or you can have it controlled by a internet connection and have these be different relays that you switch in for north, south, east, whatever, and control it remotely. But so you get 8 different positions on where to point the antenna. Oh, sorry, I didn't show this. This was well, it was there, but I didn't say anything. This is just the radiation plot for looking to the northeast versus looking towards the east. And just like in I think one of the earlier graphs, if you're broadside to the square, you get a little bit less gain, about 4.5 dB versus 5 dB, 5.4, shooting off the corners. But you get a huge front to back. So you have this big gain in the front, and you have almost no gain in the back. So people behind you, their signal strength would be way down, which is the whole point. So I think, yeah, that was my last slide. That was pretty quick, but does anybody have questions? More questions?
Three phases, yeah, 8 correct.
Yeah, so a lot of people that I saw on YouTube, they'll just buy the DX Engineering setup, and that gives you 4 directions. But if you want to get all 4, you have to build the hybrid coupler. All 8, I'm sorry. Yeah, you got to build it. Maybe there's somebody out there that builds it. Yeah, that might not work so well.
So could you in theory build like a 160 on this tube, just make a bigger square?
Oh.
And continue it out?
Absolutely, good question. So this is when you design this 4 square, you're designing it for a specific band, because the antennas have to be physically spaced at a certain distance. Most people choose a quarter wavelength. So 160 would be twice as big. So
But
instead
you
of,
could use the same infrastructure, is what I'm saying, right? Like those feeder lines that went out, those 75 ohm, if you just keep going.
oh, keep extending out,
Yeah,
and have
just
one
those-
nested inside of the ear.
Yeah.
I would bet what you'd have to do is, I think that would work. You could do them nested, but you'd have to add some additional switching so that the band that you're not using, so if you're using 160, the biggest one,
Right.
you'd have to set up switching so that you could open circuit each vertical.
Also, you
On the
disconnect
inside.
80.
Yeah, so disconnect all the 80s or the 40s or whatever you have inside, so that they don't couple to the transmitting antennas. Yeah. Yeah. So yeah, I mean, you could do it. It's just a lot more switching and a lot more control.
Then where do you take that 40 acres? It's gonna go for 300.
Yeah, you could build a second one next to it. Yeah, because I mean, this is 1 acre.
Right.
And so 160, it's 4 times that, so it's 4 acres basically. It's 4 times as big for antennas. So
Do they do something similar to this with AM stations? When they need to steer?
actually, that's a good point. So this this is what Bill put together way back in the 50s or 60s, and he was an RF engineer for AM stations, and so this was his bread and butter. was setting up AM stations, with either 2 or 4 antennas and phasing them so it points to a populated area.
Right.
Yeah. Now, they wouldn't necessarily use a 4 square configuration.
They would use something for
They
whatever the geography was.
Yeah, so they would use either 2 antennas or 4 antennas, but the 4 antennas usually would be in a line. So that then what? Yeah, you probably could. You probably could take one out, and you could do a lot of
And
things.
they steer.
They steer it.
That's the point.
Yeah.
Hey, James, can I inject a point of interest here?
Yeah, sure.
Yeah, go back to that The one that shows the full switching,
So,
that one
This
right
picture.
there. Okay. If you look at that, there was a guy named Ruthroff that did a whole bunch of theoretical work on transmission line transformers way back in the 50s or 40s or sometime.
okay,
And it turns out we were building some of these for special use in the cable TV industry back 20 years ago before they went
Oh,
to all
nice.
digital. And if you look at TR11 there, if you wound that with a twisted pair that had a characteristic impedance of your line, in our case it was 75 ohms, then you didn't need the capacitors on both ends, and it would give you an impedance match. And what you have is a directional coupler very similar to the circuit that's used on these inline Viswar meters.
Yep.
So with the right turns ratio, you get straight through is minimal loss, but with a 3 dB coupled loss going downward off of C1, that if that's down 3 dB, then the energy's got to come from someplace, and the straight through is going to be down 3 dB. And if everything's matched up, there's nothing going down the other port. And the other
the
port,
dummy.
the dummy load, and that's the port that you put the indicator on to read how much of a mismatch that you have on the test port.
Exactly.
So it's the same thing. The problem is that the transformers we were building with twisted pair were only designed to carry 15 milliwatts or something like that. So we didn't care about power handling. For power handling, they've got to wind TR11 to handle the power, and then they need C1 and C2 to give you the impedance match across that transformer, and that's why you get a narrow band effect. Ours were broadband. Ours worked from 50 to 1,000 megahertz, but this is only going to be a few megahertz wide because of the LC hard components there.
Yep. Yeah. So great points. That T1 transformer is about as big as my fist. So
at least, yes.
In order to, and a couple of cores so that it'll handle 1,500 watts.
The ones I was building were like a 3/16 by maybe a quarter. Actually, no, they were smaller than that. So, but it was very low power.
Yeah. So you're absolutely right. You can hook up a remote power meter to that dummy load out there at the hybrid coupler and monitor it. In fact, they're showing here, they're using a little induction to measure that current and feed it back to the shack. So you can, it doesn't have to be an absolute reading, but it gives you a nice relative measure of, oh, everything's in balance or something is way off. One of the antennas is lost a connection, or it's starting to corrode, and you need to go out and check things. So I thought this was interesting, and I have an interest in building one of these. So maybe one of these days I'll actually get to put it together and test it out. Although I already have DXCC on 80 meters. I think I have 134, but I got to get the other 200 and something. There's 200 people left.
Two sides of that grounded together. What about the outlet? Why did it have to be grounded?
Oh, why aren't the radials in the other directions grounded or tied together?
They're not long enough.
They give you grounded.
They're not. It doesn't go all the way around the world, so they don't come back to each other and connect. We need 24,000 miles of wire.
Times at least 100.
I suppose you could tie them together out there. The reason that they gave for putting bus bars in and tying the radials in the middle together at that point was because if you had a little bit different grounding situation at each antenna and you start overlapping ground radials, because most likely you're going to buy insulated wire. And so now you have this different ground, the different radial fields will be at different voltage potentials. And so that'll mess with the phasing that you're trying to feed the antennas because they're all different now.
It's more a matter of them overlaying each other than it is being out at the end.
Yeah, it's more of making sure that the entire field, all 4 sets of radials, are one electrical potential.
Are you gonna lay them on the ground, bury them?
Yeah, don't know. I guess it depends on how much work it is to put them into the ground.
Get a little tiny tractor.
I had some friends ask me that too. It's, oh, you don't think Kubota?
Yeah.
Nah.
Skid steer, but.
A skid steer? I looked at those. Those are kind of expensive compared to a tractor. Yeah, but yeah.
Yeah, you just build the whole thing and then haul in a truck full of dirt and just raise the ground level an inch or two. Then
Yeah,
they're
spread
buried.
it out over the top. That's much easier. I like your thinking, Dennis. That's much easier.
Jump there, we just spread that.
Spread the junk over the top. Yeah, tons of glass everywhere. Yeah. So that's all I had tonight. I hope you enjoyed the presentation. Does anybody have any other questions or comments or
You're gonna build an 80.
yeah, so I'm planning to build an 80-meter version. 40 meters, I have a 2-element beam that I'll put up, and 160, you pretty much have to build the whole thing yourself. DX Engineering does sell a 160 antenna. It's not full height. It has a capacitance hat. So it's one of these antennas that they then put copper wires onto it, about I think 35 feet. So it makes a capacitance hat over the top, and so it's a shortened vertical for 160. So I've been debating, do I want to put that up or do I want to go to the trouble of building a tapered tube for 160? And I don't know, maybe it'll be 5 or 6. Yeah, it's got to be a quarter wavelength, which at 160 is like 135 feet up in the air.
Yeah.
So, I mean, does that mean I have to?
Like this.
Yeah, exactly. Do I have to have the base tube? Yeah, exactly. Is it going to be, 6 or 12 inches in diameter? In order to be able to, and then he used towers.
Yeah. I was gonna say,
So Milt used Roam 25 tower sections and went up whatever it is.
So did he put a conductor up through the center or did he just try to?
No, he used the tower. So he insulated the base from ground with tires, and then used guide ropes to tie it all down.
Yeah.
And so he radiates from the tower
A
itself.
lot of tower stuff.
We have 5 40-foot towers. So yeah, they're a little too long. Well, yeah, they're a little too long for 40 meters. A torch. Excuse to buy more stuff. Yeah.
Makita makes a lot of wheels.
Yeah, right. Yeah, chop saws. Yeah. So anyway, that's what I'm thinking for an 80-meter antenna. And it's what got me interested to, I got to learn about it anyway. Let's put it together for a presentation and see what people think. So anyway, thanks for coming tonight. Oh, did somebody, Mark Christensen, do you have I see you got your hand raised.
Yes, I do, for just a moment there, James. What's the possibility of getting the specifications of the diagram for this? I'd like to look at this a little closer. I've got some space here. I got almost 3.5 acres, and of course I got the house on the eastern third of the property, but I'm thinking about the backyard area.
Oh,
Uh,
yeah.
I'd like to get a little more detail on this. And is it possible to get some of these slides in your presentation that shows the actual pictures and diagrams? Could you send those to me?
Yeah, I can send it to you. Is your email on your QRZ page?
No, it's not. Can I give it to you now, please?
Yeah, let me
Or,
well, you know
or
what? My email is on my QRZ page. Can
yeah,
you
and
just drop me an email?
I'm showing it. I show an email of Jay Wasson, and then the rest of it is a cox.net.
Yeah, jwasson1@cox.net.
How
Yeah,
about if I
just send
just
it
send
there.
you an email?
Yeah, that sounds great.
All
Yeah,
right, thank you.
this we're recording this presentation, so at some point in the near future, I'll upload it to the ARA YouTube channel. So it can be viewed many, many times if you like.
All
But I'll be
right,
sure, I'll send it to you, Mark.
thank you.
Oh, you're welcome. Any other questions, comments? No? Okay, well, thank you very much for coming tonight. Uh, it's been very interesting, and this was a good project. This is a good one to think about and to actually try to understand how this all works. They used to have in the ARRL handbook, they used to put the phasing table for a foursquare. And they would give you, just like Bill Orr had in his book, except for his is only for 2 verticals. But ARRL handbook used to have a phasing table for 4 squares. It's not in there anymore. So I have to go find an old handbook, maybe from the 80s, that would have it in there. But maybe at the next Hamfest. So
The prices of them just went up.
did they? Yeah, I'm sure they did. So thanks everybody for coming tonight. Greatly appreciate it. And we hope to see you all next week or next month rather, at the next ARA meeting. And hopefully I find somebody that's willing to come and present a topic other than me. But if not, I'll try and find something different and unique to share. But thanks everybody. Night everybody. All right. Take care.
Night, everybody.
Taking it to conference, and we always try to tell you how to finish it up.